Hello everyone. In the previous session, we have learned about what Gini impurity is and how we have calculated the weighted Gini impurity in order to understand what is the right feature split among the different feature splits that we have tried to evaluate. So that's the whole exercise that we have conducted in the previous session. Now let's look at understanding what entropy is and how we are going to leverage entropy and do entropy related calculations in order to understand what could be the right feature split here. In order to better understand it, I basically have come up with these two different subnodes, one on the left hand side and the other one on the right hand side. Left hand side one does indicate that it is purely non-homogeneous in nature. That is, it's perfectly an impure node. Whenever you are trying to calculate the Gini impurity for this particular subnode, it's going to result in a maximum possible value of 0.50 as we have already understood. So similarly, whatever I'm trying to understand here is to look at how far away this right hand side subnode is from this probability distribution. Like let's say that the probability distribution of this subnode, the data distribution for this subnode is going to be Q of X and this here is going to be P of X. So all what I'm trying to understand here is how different is this probability distribution P of X from this reference distribution. I'm calling this as reference distribution basically because this is the worst possible scenario that we can understand. So what could be the worst possible scenario? So the ultimate objective of the decision tree, as we have learned earlier, is to split the data into different subnodes. The subnodes are basically as homogeneous as possible. So the worst possibility situation can incur only when you have equal number of positive labels as well as negative labels in each subnode. And that's what we are observing here. The reference distribution that we have considered for solving this case is a worst possible scenario that one must encounter. All what we are trying to do here is to find or to look at this particular probability distribution P of X and understand how far away it is from the reference distribution. It has to be as far away as possible so as to state that this particular node is going to be as pure as possible. The farther away from this particular reference distribution, it is said that it's going to be pure node or homogeneous node. It will be quite far away only when you have all positives or all negatives in P of X rather than what you are currently observing. Still, P of X is quite far away from Q of X in terms of homogeneity. So there is a particular concept that we have learned in statistics which is called KL divergence. So KL divergence helped us assess how similar or how dissimilar probability distributions are, isn't it? So it was actually given by this particular formula. So we are just trying to assess the probability distribution which is given by P of X with reference to Q of X as I have represented here, which is given by summation of small k is equal to 1 to capital K, P sub k log of P sub k by Q sub k. So this is a formula that we have learned earlier. So for those who do not understand how we have arrived at this particular formula, let me break down this for you a little better. Okay. So we are trying to assess or take the difference between this distribution with respect to the reference distribution Q of X. So P of X here is the distribution for which we need to understand how far away it is from the reference distribution, right? So let me apply log to this whole term. Applying log will result in log P of X minus log Q of X. So we already are aware of this particular formula, that is log A minus log B is going to be log A by B. On the same lines, it's going to be log P of X by Q of X. And that's what we are observing here in this particular KL divergence formula. And how did we arrive at this particular summation term is what we need to understand further. So KL divergence is all about trying to understand the average deviation of this distribution P of X from the reference distribution Q of X. So we are looking at finding the average deviation of P of X from Q of X. So when I say average deviation, it's going to be the weighted average. And that's what it is. So Pk or P sub k here is nothing but the individual weights that we observe. Out of the total number of observations that you are having, how many of them does belong to positive out of the total? So that's going to be one of the weights here. And that's how you just need to intuitively understand that average deviation here corresponds to this particular summation term that we have represented here in the KL divergence formula. Right? So from this, we intuitively understand that higher the KL divergence value is, more homogeneity is there in this particular subnode S2. Let's call this as subnode S1. The left hand side one as subnode S1, the right hand side one as subnode S2. We observe higher KL divergence in between P of x and Q of x. That essentially means that S2 is going to be as homogeneous as possible. If the KL divergence is 0, if the KL divergence value that we attain is 0, then it indicates that both the distributions are one and the same. In this specific case, we clearly intuitively understand that both the distributions are not same, and hence KL divergence is not going to be equal to 0 here. I believe we understood on how we arrived at this particular formula for KL divergence. So this forms the basis for understanding on how you get entropy or how you calculate entropy for the given data. Okay. So with this as a background, with whatever formula that we have deduced, it is summation of small k is equal to 1 to capital K, P sub k log P sub k by Q sub k. So P sub k here is nothing but P of x that we have dealt with. Q sub k is going to be Q of x that we have dealt with in the previous slide. So now let me redraw this particular worst possible scenario, which basically had equal number of positives as well as equal number of negatives here. So this does indicate that the probability that it would be labeled positive is going to be 0.5, and the probability that a randomly picked point from all of these points, it belongs to a negative class, is going to be 0.5 again, which is nothing but 1 by capital K. So capital K here is nothing but the number of classes. In this specific example that we are trying to solve, the number of classes is 2 here. Okay. So now let us use these particular values within this particular formula. So Q sub k, this is all about the reference node. This is a reference data distribution. The reference data distribution that we have considered in this particular exercise is a worst possible scenario where we observe equal number of positives and equal number of negatives here. So Q sub k, since it's a reference distribution, it's going to be equal to 1 by k as we have dealt with calculation here. So I'll rewrite this particular formula as summation of small k is equal to 1 to capital K, P sub k log P sub k by 1 by k. Okay. So log a by b can be written as log a minus log b, as we have already learned. So let me rewrite this whole term as summation of k is equal to 1 to capital K, P sub k log P sub k plus, it's going to be minus summation of small k is equal to 1 to capital K, P sub k log 1 by k. So if I take this inverse of this 1 by k, it's going to be a positive here. So summation of k equal to 1 to capital K, P sub k log P sub k plus summation of small k is equal to 1 to capital K, P sub k log k. So 1 by k, I can rewrite it as k to the power of minus 1. So this exponent will now become coefficient. So minus 1 multiplied by minus is going to result in plus here. So log k, as we can understand, is clearly a constant value. And we also know that summation of all of the probabilities that we are having tends to 1. So sum of all probability values for the given data is going to result in a value of 1. So this clearly is a constant term on the right hand side that we are observing. So all what we are bothered about is this particular term now. So we are looking at a maximum possible value for KL divergence. So if there is a maximum possible value for KL divergence for any given subnode S2 with reference to this particular worst possible scenario, which is represented as Q sub k or Q of x here. So whenever you attain a maximum KL divergence value, it does indicate that whatever node that you are trying to assess is actually as homogeneous as possible, which is quite far away from the reference distribution where we observe equal number of positives and negatives. So we are trying to maximize this particular term here. So this function summation of k equal to 1 to capital K, P sub k log P sub k is what we are trying to maximize here. I can also minimize minus summation of k equal to 1 to capital K, P sub k log P sub k. So maximizing summation of k equal to 1 to capital K, P sub k log P sub k is same as minimizing minus summation of k, pk log pk. So just added this minus term so that maximization gets converted to minimization. So this is what we already have understood in detail about. So now This formula that you are currently observing is a formula for entropy. So we have attained at this particular entropy formula by gaining an intuitive understanding at the first for the use case that we have discussed, and then try to derive what KL divergence is, what the formula is, use that KL divergence formula in order to arrive at this particular entropy formula. We also have understood that maximizing summation of pk log pk is going to be same as minimizing minus summation of pk log pk. So we are going to make use of this particular formula in our subsequent session to identify what could be the right feature split for the set of feature splits that we are going to evaluate. Okay. For this particular example, for this particular reference data that we have considered so far, so P sub 1 is 0.5 and P sub 2 is 0.5. Let's plug in these values in this particular formula. So I can expand that formula as minus P1 log P1 minus P2 log P2. So it's going to be minus 0.5 log 0.5 minus 0.5 log 0.5. It's going to result in a value of 1. If you compute this value, it's going to result in a value of 1. So this non-homogeneous node will result in an entropy value of 1. So whereas the Gini impurity that we have calculated for the particular subnode resulted in a value of 0.5. So 0.5 was a Gini impurity that we have calculated for this type of reference data where we have observed equal number of data points with positive as well as negative labels. So this was a maximum possible value. For entropy, the maximum possible value here is going to be 1. So as we can clearly understand, if we come up with this particular graph where the probabilities are represented on x-axis, and obviously this is going to be an impurity function that we are representing on y-axis, the maximum possible value at 0.5 probability, that is for a non-homogeneous subnode, is going to be 0.5 on y-axis. So this is what we have understood for Gini impurity. So this was your Gini impurity. So now we understand for entropy, this curve is going to find its maximum for a non-homogeneous node at a value of 1 here. So this is going to be a value of 1. So please understand this particular difference in the values, the maximum possible values for both entropy as well as Gini impurity. So in the next session, we are going to mostly discuss about how you calculate the weighted entropy value in order to understand what could be the right feature split. So these are 3 different steps which we can incorporate in order to find the best feature split. First, we'll calculate the entropy of the parent node as well as entropy of the child node. Finally, look at computing what could be the weighted average entropy of the feature split. Just like we have computed weighted Gini impurity in order to understand if the feature split is the right feature split or not. We'll also calculate weighted average entropy value in order to assess if the feature split is the right one or not. Okay, cool. So that's pretty much all I wanted to discuss in this session, and see you in the next session.